Global warming is exacerbating the problem of hot regions of the planet suffering from a lack of fresh water. Millions of tons of desalinated water per day, obtained using, for example, reverse osmosis, would seem to solve this problem, for example, in the Gulf countries. However, behind the appearance of success of effective desalination technology, there is also a growing problem of maintaining ecological balance after discharging salt-saturated water back into the sea. The discharged brine sinks to the bottom of the sea, displacing oxygen and killing living organisms that find it difficult to adapt to their new habitat. At the same time, North Africa and the Arabian Peninsula are suffering from desert dehydration, which is only growing in size. Is it possible to solve both of these problems simultaneously by harnessing the nearly unlimited solar and wind resources in these regions? Perhaps yes, it is possible. Moreover, by solving the problem of recycling salt water to obtain fresh water directly in the desert, the technology makes it possible to organize landscaping of the desert, as well as an extensive greenhouse economy, which, simultaneously with the environmental problems of the onset of deserts, will also solve the problem of food. And this will not require huge investments in complex, expensive structures and installations, and there is no need for special, high-tech materials. And the first thing that needs to be done is to demand that the owners of desalination plants, using, for example, reverse osmosis, refuse to discharge waste salt solution, which is toxic to the environment, into the sea and direct this flow through a pipeline to the most arid and hot regions of the desert. This main pipeline will supply salty wastewater to numerous small oases, where it will be processed to produce fresh water and dry salt using multi-stage evaporation. And since greenhouse farm owners who process brine from desalination plants into fresh water and dry salt solve important environmental problems, they do not have to pay for the salt water they receive through the main water supply. In this case, there will be mutual benefit for both the owners of desalination plants and the owners of greenhouse farms, oases in the desert. The key element for organizing oases along the entire length of the main salt water pipeline is multi-stage evaporation technology based on film evaporation drums. It is this technology that allows for complete separation of the incoming brine into fresh water and dry salt using solar energy and, possibly, wind for this purpose. Obtaining sufficient quantities of fresh water in evaporation plants in the presence of electricity makes it possible to organize large, but water-efficient greenhouses, which solves not only the food problems of the region, but also employment problems. The presence of abundant solar energy makes it possible to provide organized oases with autonomous sources of power supply, although there are no difficulties in ensuring centralized power supply along the entire route of the main water supply. And perhaps it will even be more cost-effective than autonomous power supply systems. The minimum configuration of the created ecological system of oases must include the following elements. An artificial reservoir in the form of a deep pool, filled with salt water from the main water supply, which acts as a heat accumulator to ensure a comfortable operating mode for greenhouses. In addition, this basin is a source of feedstock for a multi-stage desalination plant. Venturi scrubbers provide optimal temperature conditions in greenhouses and cooling of pool water during hot periods when operating in cooling tower mode. A greenhouse that maintains a comfortable temperature regime using the thermal energy of a salt water pool and irrigated with fresh water obtained in multi-stage evaporators. A large freshwater storage tank located underground, which collects condensate not only from the evaporators, but also condensate from humid night air from the Venturi scrubber, pumped through the greenhouse during the cold night hours. And finally, the key element of the mini oasis technology is a multi-stage solar desalination plant based on a completely new type of evaporation apparatus, film evaporation drums, which allows you to forget about the problem of salt deposits on heating surfaces during evaporation. Let's consider the operation of the key element of the mini oasis project, a solar multi-stage desalination plant based on film evaporation drums. The installation works during the day, but preparation for work begins at night. To do this, from the lower part of the pool, where the salt concentration is maximum, brine is pumped into a 30 cubic meter tank of the initial solution to the required level, then the tank is sealed. The volume of water in the pool is compensated by the supply of salt water from the main water supply. With the beginning of daylight, the air compressor is turned on, supplying air to the source solution tank, and the pressure in the tank rises to 4 atmospheres. This allows the film evaporation drums to be fed when the liquid level in them drops during water evaporation. The replenishment process is controlled by a float valve installed inside the drum. The solar desalination plant uses 2 types of film evaporation drums. In drums of the first type, liquid evaporation is produced by solar energy focused by a parabolic reflector onto the outer surface of the drum. At the same time, the drum rotates, and its entire surface is heated evenly. Since the surface is constantly wetted from the inside, intense film evaporation occurs, and the generated steam is directed to the first stage of the heating steam jacket of the second type of film evaporation drums. The design of these drums is somewhat more complicated, but this allows the use of a multi-stage thermal distillation process. As in film evaporation drums of the first type, a coiled rod rolls under the liquid level in the drum, which does not allow deposits to form on the inner surface. The difference between drums of the second type and drums of the first type is that they are heated due to the condensation of steam on the outer surface. Condensate accumulates in the lower part of the housing and, after passing through a thermodynamic condensate trap and heat exchanger, is sent to a fresh water collection tank with a volume of 100 cubic meters. Steam, condensing on the outer surface of the drum, gives off heat, which goes to evaporate the liquid film on the inner surface of the drum. Secondary steam is generated at a lower pressure and temperature than the heating steam. The secondary steam becomes heating steam for the next stage, and so on. The heating steam of the last stage is sent to the air heat exchanger, where it condenses, raising the temperature of the pumped air to 100 degrees. This hot and dry air is used to dry the salt concentrate fed to the conveyor. The dried salt enters a bunker, where it is accumulated and periodically unloaded. 3 parabolic solar reflectors with a total reflective surface area of 210 square meters on an average day provide thermal energy supply to the first type drums at a level of 6.5 kilowatt-hours per square meter and produce about 2,200 kilograms of steam. Taking into account the subsequent 5 stages of desalination in film evaporation drums of the second type with a diameter of 0.5 meters, a length of 6 meters and a wall thickness of 2.5 millimeters, the amount of steam produced in the desalination unit increases to 12 tons per day. After condensation, this steam is drained into a fresh water tank. On cloudy days and in winter, the amount of desalinated water will be noticeably less, but in deserts with hot climates it is very important that this is a stable source of fresh water, provided that the losses of the process basin are replenished with salt water from the main water supply. When using the Venturi scrubber correctly, additional condensation can be added to the fresh water tank by introducing humid air into the cooled greenhouse at night, which will lead to condensation on cold surfaces. The most important issue regarding the efficiency of desalination is the energy cost of the technology used. Since the technology is aimed at application in regions with a hot, arid climate and a large number of sunny days with high levels of insolation, this significantly simplifies its implementation based on renewable and environmentally friendly energy sources. This applies primarily to solar energy, although wind energy can also be used. However, it should be borne in mind that large wind generators are much more difficult to maintain compared to solar panels, and therefore require more highly qualified operating personnel. In the presented design of a mini oasis, the autonomy of the energy system is ensured mainly on the basis of solar panels with photoelectric converters. Wind energy is used only to ensure the continuous rotation of the drums to constantly clean the heating surfaces of deposits in a multi-stage evaporation plant at night, when the energy obtained from solar panels must be saved. To ensure that the gear motor, which ensures guaranteed rotation of the film evaporation drums during the daytime, and the wind engine do not interfere with each other, the rotation drive is equipped with a differential mechanism. During the daytime, their rotational frequencies are summed up, and at night, the rotational frequency of the drums is equal to the rotational frequency of the wind engine. Despite the possibility of complete autonomy of the mini oasis power system, the most likely and preferable option will most likely be a centralized power supply via an electrical network built along the main salt water pipeline. This also applies to logistics, since the presence of a highway will ensure timely delivery of greenhouse products to the consumer and thereby ensure the competitiveness of the project. A feature of the proposed greenhouse design is that they have a comprehensive cooling system. The refrigerant can be either salt water from the pool or fresh water stored in an underground tank. If the pool depth is sufficient, the water temperature at different depths can vary significantly, which allows you to regulate the temperature of the cooling water in the condenser heat exchanger located in the upper part along the entire length of the greenhouse under the solar reflector. Between the inlet and outlet manifold pipes of the heat exchanger condenser, running along the entire length of the greenhouse, there are coils of air cooling tubes with transverse fins. Moist heated air rising to the upper part of the greenhouse enters the area of finned heat exchange tubes, on which moisture condenses, and the air cools and falls down. With a small hydraulic resistance of the finned tubes, the air in the greenhouse is cooled quite effectively even in very hot weather. Drops of condensation from the finned surfaces of the cooling tubes fall into a slightly inclined tray and are directed by gravity to an underground fresh water tank. At the exit from the condenser heat exchanger, the heated water is supplied to the Venturi scrubber, where it is sprayed into a restriction device, entraining hot atmospheric air with low humidity. At the same time, the air is humidified and cooled, and due to evaporation, the circulating water is also cooled and sent back to the pool, but with a slightly increased salt content. The air, cooled and saturated with moisture in the scrubber, can be directed both into the atmosphere and after passing through the droplet eliminator into the greenhouse. The optimal ratio between these flows depends on specific atmospheric parameters and time of day. From an underground storage tank, part of the fresh water is drained into a container, where it is saturated with substances necessary for plants and then sent by pump to the greenhouse, either in the form of drip irrigation or in the form of drip mist that effectively cools the air. The removal of moisture from the greenhouse is determined by the ventilation flow rate and the difference in the moisture content of the air at the entrance to the greenhouse from the scrubber and the exit from the greenhouse. This difference is easily compensated by desalinated water obtained in a solar desalination plant. Since the productivity of solar desalination plants exceeds the needs of greenhouses for irrigation, excess fresh water can be used both for household needs and for drip irrigation of plants in open areas, ensuring the production of additional agricultural products and landscaping of the surrounding area. Perhaps, from all that has been said, questions remain as to why film evaporation drums provide the creation of a technology for the complete separation of brines into clean water and salt. It's all about the heating surface cleaning system. Typically, cleaning is carried out only when the heat transfer has become unacceptably low and when the technological process is simply forced to stop to remove salt deposits from the heating surface. In this device, everything is different. The technological process of heat transfer through the wall during evaporation on the inner surface of the drum and condensation on the outer surface, as well as cleaning the inner surface from salt deposits, occur simultaneously. When the drum rotates, which is necessary to create a film of liquid, a spiral wound rod simultaneously rolls under the liquid level in the drum under the influence of gravity. Since it cannot move axially, the spiral coil acts like a screw, moving the resulting salt sediment to the point where the concentrate is discharged from the drum. Therefore, the film evaporation drum has practically no restrictions on the degree of concentration of the solution, and it becomes possible to unload from the drum a saturated solution with a high salt content, in which there is very little water, and the residual water can be removed to obtain dry salt quite simply, by blowing hot air. As a thermal physicist, I believe that the project of a mini oasis in the desert is quite feasible. But here's the question: how much will all this cost? Before you answer, you need to clarify your goal. If the goal is an energy-independent greenhouse with an area of 1 hectare, then 3 solar desalination plants are enough, which will process about 40 cubic meters of brine per day from huge desalination plants on the coast, and receive an average of 30 cubic meters of fresh water per day. In this case, the minimum estimated investment value will be about $850,000. If the goal is not only greenhouse farming, but also maximum volumes of recycling harmful brines, and the goal is also the greening of the desert, then the number of solar desalination plants should be increased, for example, to 10 installations. This will allow at least 70 tons of fresh water per day to be used for landscaping the desert and for the production of agricultural products in open ground with drip irrigation. At the same time, the volume of recycled brine will increase to an average of 130 tons per day, and the minimum investment cost will increase to $1,250,000, which, however, is not too different from the first option. And still, the fantastic volumes of harmful brine dumped into the sea cannot be exhausted. To utilize only 10 million cubic meters of brine discharged into the sea per day, 77,000 farms with a greenhouse area of 1 hectare will be required, which, with an average capital investment in greenhouse farming of $1 million, will result in a huge amount of $77 billion. But these costs are not irretrievably lost. If we assume that by creating optimal conditions in greenhouses, 50 kilograms of agricultural products will be produced per square meter per year, then with the cost of selling these products $1 per kilogram, a successful farm could earn $500,000 in a year, and, at the same time, not only provide a solution to food problems, but also green the environment, thereby possibly counteracting global warming. If in these 77,000 farms, on average, greenhouses per square meter produce 25 kilograms of products per year, then the result is also a huge figure: 19.2 billion tons of agricultural products. Thus, by simultaneously solving the problem of land desertification and the discharge of brines after desalination, the food problem can also be solved. Of course, even by rough estimates this is a fantastic investment, but perhaps preserving the fragile ecology of warm seas and greening deserts is worth it.